This second chapter in our course on statistics for data scientists will be a very short one, but a crucially important one, because here I will introduce the histogram. Now you might already be familiar with the histogram. Nonetheless, I recommend watching this lesson just to refresh your memory, get you on the same page, but also because there are some very neat animations that will help you remember this material better. So let's get into the slides. And let me start by explaining why it is justified to devote an entire chapter to the histogram. And the reason is twofold. The first reason is that the histogram is the most used visual tool for any data scientist. And therefore it is worthwhile to know where it comes from, how it is built, and what it actually represents. The second reason is more specific to this course, namely that all subsequent chapters heavily rely on your knowledge of the histogram to explain more abstract and complex concepts in statistics. And by doing so, you will get a more intuitive understanding of these concepts. Now that we understand the importance of the histogram, let's look at what it actually represents. In a nutshell, the histogram is a visualization of your data distribution. And the distribution of your data, in turn, answers the question, how many times do I observe data in this specific range? Now this might sound abstract, but be sure that it will be much more clear once we start building our own histograms. Now once we have our histogram, what can we actually get from it? Well, the first use case is a very practical one. By simply looking at the shape of our histogram, we can derive some general properties of our distribution. Let's take this histogram as an example. We see that all of our values lie between the value 0 and the value 5. However, most of our values are clustered around the value 1. And we can also observe immediately that our data is skewed to one side. What does this mean? Well, it means that even though our data lies between 0 and 5, the vast majority of our data lies between 0 and 2. And these are all qualitative properties of our data distribution, which we can derive by simply looking at the shape of our histogram. Now, the second use case, which I talked about earlier, is that the histogram can serve as a building block for more complex concepts in statistics. For instance, the p-value, which is oftentimes considered a very abstract concept, can be made very visual and thus intuitive with knowledge on the histogram. So now that we roughly know what the histogram is and what we can do with it, let's learn how to actually make a histogram. How do we actually get this histogram from our own data set? Now, to build a histogram, in general, we go through 4 steps. The first step is to collect data. The second step is to make data bins. The third step is to assign each data point to its corresponding bin. And then the fourth step is simply to stack blocks. Now, to make these 4 steps more concrete, we will go through them step by step in an example. And for this example, I made an animation that is available to you to download as a separate file. So let's dive into it. The first step is to collect data. In our case, each data point corresponds to a person's height written down in centimeters. Step number 2 is to make data bins. Now, a data bin is basically a small data interval with a lower and an upper bound. And what we have to do is to choose the size of this data interval. The bin size in our case, we choose to be 5 centimeters. And to implement this bin size into our data, we basically take the entire data range and we chop it up into buckets. And each bucket will have the same bin size, which for our case is 5 centimeters. Then step 3 is to assign each data point to its corresponding bin. For instance, 179 lies between 175 and 180. And then the fourth step is to stack blocks. This means that each time we have multiple data points corresponding to the same bin, we just stack them on top of each other, such that in the final histogram, the number of blocks represents the number of data values that got assigned to this bin. And after these 4 steps, we have our histogram. Now, I agree that this histogram of 10 points doesn't look all that appealing, and we wouldn't want to draw any conclusions from it. Even though in later chapters we will learn how to draw conclusions from datasets with so few data points, we will see that such conclusions will come with a very large uncertainty. Instead, what we will do here is take the better strategy. Just collect more data. And then we just go through the same steps. We collect data, we choose a bin size, but here we already have a bin size of 5 centimeters. Third step is to assign each data point to its corresponding bin. And then the fourth step is just to stack blocks whenever we have multiple values for the same data bin. And at this point, we see something magnificent. Even though each data point on its own doesn't tell us anything about the distribution, when we bring them all together, we see a general pattern emerge. And this pattern is, of course, the histogram of our data. Now, as a final step, we can remove the lines separating different blocks. And then we get the familiar side of the histogram, where the height of each bar corresponding to each data bin is proportional to the number of values that got assigned to this data bin. So now that we know how to make a histogram, what can we actually learn from this? We can immediately observe that we can draw some more conclusive insights by looking at the shape of our histogram. For instance, in our example, the bin from 180 to 185 clearly has the most data points assigned to it. And if we go to larger values or lower values, we see that the histogram tapers off roughly symmetrically. Now we can also look at outliers. For instance, the bin from 160 to 165 only has one data point assigned to it. And these are all qualitative properties of the data distribution that we can abstract by simply looking at the shape of our histogram. Now, at this point, you might object that the shape of our histogram is arbitrary. Now, why would it be arbitrary? Well, think back to step number 2 of building our histogram, where we had to choose the bin size. And the bin size heavily influences the shape of our resulting histogram. Just imagine that we would have taken a bin size from 160 all the way to 205. Now that would mean that all of our data points would have ended up in the same bin. And the resulting histogram would just be one large bar which wouldn't have taught us anything. And this raises the question, can we find something that allows us to abstract insights into our data distribution by just visual inspection, but whose shape is independent of any of our choices? And this brings us to the probability density function, which will be the topic of next lesson.